So in question 11, the key is going to be to find the wavelength, and then if we find out what fraction of a wavelength that 50mm separation corresponds to, we can easily work out what the phase difference will be. So the first job is to use these numbers and get lambda is equal to c over f, which is 30 over 150, which is 0.20 meters is the wavelength. And then we've got to figure out what 50mm is corresponding to that. So 50mm is 0.05 meters, because it's 50 times 10 to the minus 3, so that's 0.05 meters. So that means that 50mm is equivalent to 0.05 over 0.20, which is 0.25 wavelengths. Okay, so it's a quarter of a wavelength. So a quarter of a wavelength corresponds to a phase difference of 90 degrees. And therefore the answer is B. Okay, question 12 is sort of all these ideas related to refractive index and so on. So it may well be that you can remember that the velocity of light is highest when it's in a vacuum. Remember, nothing can travel faster than light in a vacuum, and therefore the difference in the velocity when it goes into an optically denser medium must be that it decreases. So when light goes from a less dense to a more dense medium, the velocity is going to decrease, so that narrows it down to A or C. And the frequency, remember, is fixed because the frequency depends on the oscillation frequency of the source, and it doesn't change as the light moves from one medium to another. So that immediately says, because we'd already narrowed it down to A and C, that it must be C. And we can just check that the wavelength one is right, because remember that C is equal to f lambda. So if f is the same and C has decreased, then lambda must have decreased as well. So that also fits with C. So in question 13 we have this situation, and it wants to know the period of the wave. So the period of the wave is the time it takes to move through one wavelength. And so we can first work out what the wavelength is. So if we start from 0, you can see that a wavelength corresponds to moving through there and then back up to there and reaching that point, and then you're going to see start doing the same thing again. So that corresponds to one whole wavelength, and therefore that tells you that the wavelength is equal to 4 centimeters. So we can work out that, or rather it tells us that the speed is 20 centimeters per second, and obviously time taken is just distance over speed. So to travel one wavelength, that's equal to 4 over 20, which is 0.20 seconds, would be the answer for the period, which is answer B. So in question 14 we have a stationary wave, and it says, right, this is what it's looking like at time 0, and we've got to figure out what will have happened after 0.01 seconds, and it gives us this value for the frequency. So the first thing is we have to turn that into the period, the time taken for one complete oscillation. So t is just 1 over the frequency, which is 1 over 50, which is 0.02 seconds. Okay, so that means that it's going to take 0.02 seconds, say for this point, to go all the way down to there, and then here, and then there, and back up again. Because that's one complete oscillation, and so 0.02 seconds, the period is the time taken for that complete oscillation. So therefore 0.01 seconds is a half of t. It's half a period, and therefore it will have moved through half an oscillation. And what that means is that this point will have got all the way down to the bottom but not yet moved back up again. So what it's going to look like after half a period is that that's up to there, positive in the middle, and then back like that again. So it's basically everything's been inverted because it's gone through half a cycle, and that corresponds to curve C. Alright, question 15. This is actually a pretty mean question for 1 mark, but as soon as you see that it's to do with tension and frequency, that's going to be the relationship that you're going to use, which remember is there on your datasheet. And basically what we've got to do here is look at a situation where we want the lengths, we want the frequencies to be the same for these two strings. So this is going to be the same number, and we want the tensions to be the same for the two strings. And so what we've got to look at is what must happen to the length if we change mu in a particular way, because the diameter is going to affect mu. So we could, just to make it slightly easier, I guess, rearrange this slightly and just move the L over to here and the F over to there. So we get L is equal to 1 over 2F times the square root of T over mu. And then we can just sort of say, right, you know, this expresses L as a function of mu, because as I said, the rest of these things are constant in our experiment. And so we can say, well, whatever happens to mu when we change the diameter, L has to change by the same factor. So mu, remember, is equal to mass divided by length. Now if you think about a wire, you've got something like that, where the volume is equal to the cross-section area, which we'll call A, times the length. Remember, these two wires are made of the same material, so they'll have the same density, and we can say that the density is equal to mass over volume, okay, which is the same for both, which is mass over AL. So comparing those, you can see that mu is equal to the density times A. And if we're talking about a wire with a circular cross-section, then A is proportional to the square of the radius, and since the radius is just half of the diameter, that means that A is also proportional to the square of the diameter. So what I'm saying is that because rho is a constant, remember it's the same density for both, the implication of all of that is that mu is proportional to the square of the diameter, is the important thing. So then let's look at what happens in this expression. So if we look at what happens, for example, if we double the diameter, which is the case in cases A, B and C there at least, if we double the diameter, that means that mu will increase times 4, okay, because it's proportional to the square of the diameter. So what that means is that after we double the diameter, the new length, which we'll call L prime, is equal to 1 over 2F times the square root of T over 4 times the original mu, which we'll call mu naught. And that means that L prime is equal to 1 over 4f times the square root of 2t over mu naught, okay, because the square root of 4 is 2, and then 2 times 2 is 4, which means that L prime is equal to a half of the original L, because it's 1 over 4f there rather than 1 over 2f. So in other words, if the diameter is doubled, then the length has to be halved, and that's what happens in case C. So C is the answer. You can reason it in lots of ways like that, but it's all quite a lot of work for 1 mark.